Okay, welcome everybody. Today is the first seminar of the summer semester in our department. So I'm very happy to introduce Ipsita Mandal. She's from the Institute of Nuclear Physics of the Polish Academy of Science, and she's going to talk about critical Fermi surfaces. So please, Ipsita, go on.
Thanks, Francesco. So today I will tell you about some methods by which we can gain controlled access to the low energy physics of critical Fermi surfaces. Now, as condensed matter physicist, first I want to outline the fact that we are interested in the study of complex behavior of a large number of interacting particles. So it is important to realize that the collective behavior gives rise to emergent properties that were not present in the individual particles if you look at it individually themselves. Now, in particular, I'll be concentrating on strongly correlated systems. Now, to give you an intuition to understand what I mean by that, suppose we take a box of gas molecules. Then we know that gases are weakly interacting. That means the motion or the position of one gas molecule hardly depends on the position or motion of the others. But now imagine lowering the temperature when the motion of these gas molecules get more and more correlated. And this also leads to an increase in complexity of the system. Below a certain temperature, we know that there is the formation of crystals. And in some sense, this is strongly correlated because there are various kinds of excitations in the system. For example, collective motion of many atoms, which gives rise to phonons, which were not present in this individual motion of the gas molecules. Now, our strategy to deal with such systems will be to formulate some effective field theory. And why is that necessary? So first, let us realize that we are dealing with a system where the position or motion of each electron. So in condensed matter physics, we are mostly interested in the dynamics of electrons. So then the position motion of each such electron is correlated with those of all the others. And it is a problem which is hard to describe. Now, you might think that maybe we will use brute force and we will give the equations of motion in a computer and just solve them. But that will fail because the number of electrons, the density of electrons in typical materials is usually very high. So it's of the order of Avogadro number, which is 10 to the power 23. So one way of approaching towards the solution of the problem is to understand the long wavelength physics or the macroscopic properties of the system by using a low energy or infrared effective field theory, or EFT. Now, when we are talking about long wavelength, it means that the short distance information averages out, or the microscopic details of the systems are irrelevant. And many systems show similar behavior in this long wavelength limit, by which we can divide them into universality classes. Now, if we are fortunate enough to find a tractable effective field theory or formulate an effective field theory, then that is very useful because then we will be able to identify universal phenomena, like identify the universal classes or the critical scaling values and so on. And then this effective field theory model is a simpler model than the original microscopic models, which many times is very dirty due to various degrees of freedom. And then we can extract physical properties which we can relate to experimental observations. So this makes our life simpler. Now here I will focus on the systems which are called strange metals or non-Fermi liquids. And this metallic regime typically appear in materials which show high TC superconductivity. Now, to understand these non-Fermi liquids, let us review the theory of normal metals. Now, the effective theory of normal metals is given by Landau's Fermi liquid theory. So Landau observed that if we take a finite density interacting electron system, or in general fermionic system, then its properties do not necessarily depend on the specific microscopic details that we might choose to study. So broadly, there are two properties. First, there is the ground state, which is characterized by a sharp Fermi surface in the momentum space. And then about that ground state, we have some low energy excitations, which we call the quasiparticles. Now, technically speaking, Fermi surface is the jump in the Fermion occupation number n of k at 0 temperature. That means it is the surface which divides the occupied states from the unoccupied states. And if we plot the occupation number against the momentum k, we see that there is this jump, which is the location of the Fermi surface or the Fermi momentum. Now, this definition applies to both free and interacting systems, and the jump is often denoted by the symbol Z. Now, the jump is equal to 1 for a free system, and it is reduced from the value of 1 for an interacting system. Now, if we take a 3D isotropic fermionic system, then the Fermi surface looks like the surface of the sphere that I have shown here. And the radius of the sphere is given by kf, which is the Fermi momentum. Now, what are the elementary excitations of this system, which is the Fermi liquid? Now, first, let us take an ideal Fermi gas when there is no interaction between the electrons. Then the electrons and the holes are the excited state of this ideal Fermi gas. So if we just take away an electron from the field Fermi surface, that creates a hole. And if we add an extra electron, that creates an electron. So the energy of the excitation measured with respect to the Fermi energy is given by k squared by 2m minus EF, where EF is the Fermi energy of the system. Now, if we consider conduction electrons in real materials, then it is an interacting Fermi liquid. However, its excitation spectrum is similar to that of a free Fermi gas, where we can invoke this particle hole excitation picture. So we can imagine like this, that slowly as we are switching on electron-electron interaction, then an excited electron is getting dressed by a surrounding distortion, and this is coming due to the interaction. And the dressed electron is then called the quasiparticle. So this is a schematic diagram of the dressed electronic operator, electron creation operator. Now, suppose we have added an extra electron to the system and we want to compute the resulting wave function. Now, if it is an interacting system, then schematically we can represent this as the Fermi surface and then an extra electron brought close to the Fermi surface. But as soon as we switch on interactions, then of course this is not the only picture, because the added electron can now excite virtual particle hole pairs, and we have to sum over a series of diagrams as shown here. Now, by using this formalism, we can compute the Green's function, and the coherent part of the single particle Green's function can be represented like this. You see that there is a pole of the Green's in the Green's function, which tells us that there are collective low energy quantum oscillations which are long-lived, and these are called the quasiparticles. Now, the Green's function is a function of two variables. First, the energy omega, which is measured with respect to the Fermi energy, and then the momentum. Now, the component of the momentum, which is perpendicular to the Fermi surface, is measured with respect to the Fermi momentum. And then, of course, there is the parallel to the Fermi surface component, which is given by K parallel. Now, there are two parameters in the Green's function. The first parameter is the gamma, which is also called the decay rate, and it goes as the energy omega square. Since omega is equal to 0 right on the Fermi surface, this tells us that the quasi-particle lifetime diverges as we move closer and closer to the Fermi surface. Now, the other parameter is the quasi-particle width Z, which lies between 0 and 1. For a free system, it is equal to 1, and for an interacting system, it reduces from the value 1. Now, physically, this measures how much overlap there is between the elementary excitation of a free system and that of an interacting system. And we can talk about this overlap meaningfully because the ground states of the two systems can be adiabatically connected to each other. We can also prove that these quasi-particles are in one-to-one correspondence with the excitations of a free system. Finally, if we theoretically compute by using this Fermi liquid theory, or experimentally observe the temperature dependence of various thermodynamic and transport properties, then these also turn out to be very much similar to those of pre-fermions. For example, the resistivity rho goes as T square, the specific heat is linear in T, and then the imaginary part of the self-energy sigma, which includes all the correlations of the system, that goes as energy omega square. So thanks to Landau's Fermi liquid theory, what seemed to be a complicated problem due to the presence of interactions has been reduced to a simpler one. Now, which systems actually are we allowed to call as a proper Fermi liquid? Now, first, we can derive Landau's Fermi liquid theory from an interacting Hamiltonian by using many-body perturbation theory by treating the interaction as a perturbation. Now, if we draw the spectral distribution function A, first for a free system, then the excitation has this peak, delta function peak, which has weight 1. Now, if we move to an interacting system, this delta function peak now becomes a Lorentzian, and its weight reduces from the value 1. The rest of the weight is shared by some incoherent background excitations. Now, to have a well-defined quasi-particle description, we must have the conditions that the quasi-particle weight z should not go to 0, and the width of the peak, which is given by gamma, that must be much less than the typical energy of the quasi-particle, which just means that the quasi-particles must not decay before establishing their excitation energy. So if these conditions are fulfilled, then we have a well-defined Fermi liquid system. Now, what is the intuition behind the fact that Fermi liquid theory is so successful in describing normal metals? Now, first, let us observe the fact that all the electrons are negatively charged. So there is electron-electron repulsion, giving rise to screening. So this repulsion reduces the effective negative charge around each. So if we have a strong interaction like a Coulomb interaction, which is also long-ranged, due to the screening, it acquires an exponentially decaying part, which makes it tractable. Then we are familiar with this Pauli principle for fermions, which helps to reduce many-body effects. This is because the phase space for electron-electron interaction scattering in the low energy limit is quite limited. For example, let us take this electron C and then let it be at temperature T. So the excitations of this electron C will be limited within this window of kBt. So if we try to excite an electron deep down from the Fermi sea to outside, then it will cost a lot of energy. So that kind of scattering will not be applicable for the low energy. So then the phase space restriction argument is not restricted to weak interactions alone, and it helps to reduce the many-body effects. Hence, we find that in many metals, electron-electron interaction can be indeed considered as a perturbation. Now, this was the nice story of the normal metals, but we are also familiar of systems where this nice Landau Fermi liquid framework breaks down. For example, suppose we are trying to write down the low energy effective field theory for an electrons interacting with some emergent bosonic degrees of freedom. Now, if the boson is massive, then we get back this nice Landau Fermi liquid picture where we have long-lived quasi-particles. But in some situations, when the boson becomes massless, then it can happen that the quasi-particles get destroyed. And then we generically call these systems non-Fermi liquid systems. A typical example is a quantum phase transition, which is a continuous phase transition occurring at 0 temperature as a function of some tuning parameter. So there is an ordered phase and a disordered phase, and the phase transition is brought about by the presence of a bosonic order parameter, which becomes massless right at the quantum critical point. And then this bosonic order parameter can mediate strong fluctuations, which can lead to the destruction of the quasi-particles. An example will be antiferromagnetic order, Ising nematic order, charge density order, or even some artificial gauge fields or real gauge fields in systems. Now, basically in these systems, we will be treating with the critical Fermi surfaces. Now, by this statement or by this phrase, I mean that we are dealing with states which have a sharp Fermi surface or a well-defined Fermi surface, but somehow the Landau quasi-particles get destroyed. And this can be various quantum critical points associated with the onset of various kind of order, emergent gauge fields, etc., which I already told you about. Now, how can this happen that we have a sharp Fermi surface but no quasi-particles? So let us look at the origin or a possible origin of critical Fermi surface. And this can happen when the quasi-particle weight Z vanishes continuously everywhere on the Fermi surface at the phase transition point. Now, in the series of diagrams along the y-axis, I have shown you the ground state momentum distribution, and along the x-axis, there is the momentum k. Now, the first picture refers to a well-defined interacting Landau Fermi liquid, and therefore there is a discontinuity, which is equal to Z, and the position or the location of the discontinuity identifies the location of the Fermi surface. This also identifies the Fermi momentum kf. Now, let us imagine that we have transitioned to another phase in the second diagram where this Fermi liquid has been completely destroyed. So in this phase, N of k is smooth everywhere. There is no discontinuity and no notion of Fermi surface or Fermi momentum. But now imagine the situation when the first picture is changing into the second. That means Z has just gone to 0. In this case, N of k is continuous everywhere, but its derivative is discontinuous. That means the discontinuity has been replaced by a king singularity. Therefore, we can still identify the position of the Fermi surface and the Fermi momentum by locating this king singularity. But since Z has gone to 0, we can no longer meaningfully define the quasi-particles. Now, I have told you that where there is a fermion boson system where boson becomes massless, that gives us a perfect recipe to get a non-Fermi liquid system. This is because the fermion boson couplings become strong, particularly in low dimensions like 2D, even if we start with the Weir value of a coupling, which is small enough. So as we flow to lower and lower energies, the coupling becomes stronger and stronger. So this leads to driving this quasi-particle weight to 0, which means the quasi-particles are getting destroyed. Now, intuitively, we can think of this picture that when we are considering the Fermi surface much away from the quantum critical point, it looks like this calm sea. But as we are approaching the quantum critical point, then it undergoes violent fluctuations so that it looks like this violent and stormy sea. And basically what is happening is that the critical fluctuations at the quantum critical point coming from the boson, that is coupling to the itinerant electrons on the Fermi surface. And those of you are familiar with Feynman diagrams, we can then represent the electron-electron scattering as being mediated by the propagator of a massless boson. So we will attempt to describe this non-Fermi liquid systems as resulting from the interaction between a sharply defined Fermi surface and a gapless order parameter, which is undergoing violent fluctuations. Now, why should we be interested in this non-Fermi liquid systems? Do they appear in realistic materials? The answer is yes, they're quite ubiquitous. For example, whenever we look at the generic phase diagram of a high TC material like cupretes, we find this strange metal regime which show non-Fermi liquid behavior. For example, when the experimentalists measure, for example, the resistivity, that sometimes turns out to be linear in T. And then when they measure the imaginary part of the self energy, that goes as omega, rather in omega square in various R-phase experiments. So this leads us to believe that Landau quasi-particles cannot be the emergent degrees of freedom for this kind of systems. Now, that strange metal regime is believed to appear from a quantum critical point, but generically we do not see a naked quantum critical point in experiments because there is always a superconducting dome hiding it. However, if we go to temperatures above the transition temperature Tc, its presence is felt through this strange metal regime. Now, there are various experiments who have seen this strange metal behavior, and here there is such an example of experimental results. So there is a heavy fermion compound for which the resistivity is being measured. The resistivity is found to be varying as t to the power 1 in this orange region or linear in T, and then it goes as T squared in the blue regions, which is the usual Fermi liquid behavior. Now, all these experimental observations lead us to argue that we indeed need a calculational framework beyond the Fermi liquid theory. Now, typically, we condensed matter physicists, when we want to write down the quantum field theory of metals, this is harder and less well understood compared to the relativistic quantum field theories that we find in the textbooks. Because in this condensed matter systems, we have lower amount of symmetry, and then we have this extensive number of gapless modes, which have to be kept in the low energy effective action. So as theorists, we want to explain these strongly interacting systems in a controlled framework, in a controlled approximation. And fortunately, we were successful in developing a novel analytical framework where we use the tools of quantum field theory, tools like dimensional regularization and renormalization group. And our controlled approximation allowed us to compute various physical properties like critical exponents, optical conductivity, and so on. Now, let me try to explain to you intuitively this idea of dimensional regularization. Let us start with an isotropic 2D metal, which has a Fermi surface, which looks like this red ring. And suppose it is undergoing violent fluctuations. Then the probability of this black dot of getting hit by these fluctuations is quite high in 2D. But now mathematically, we can suppress these quantum fluctuations by adding some extra dimensions perpendicular to the Fermi surface. So the second picture shows the same Fermi line, but now embedded in a 3D momentum space. Due to this 3D momentum space embedding, it can now fluctuate in two mutually perpendicular directions. So now the probability of this black dot of getting hit by the fluctuation is lower than it was in the 2D case. So basically, this is due to the reduction of the density of states as we increase the dimension of the system. Now, this is a well-known concept from statistical mechanics and quantum field theory. And through this mathematical method, our aim is to find the upper critical dimension DC such that if the physical dimension of the system is greater than DC, then it will be well described by a mean field theory, in this case, a Fermi liquid theory. However, if the actual physical dimension of the system is less than or equal to DC, then we cannot trust the universal critical scalings coming from a mean field theory. However, now we can carry out a controlled perturbative expansion in this small parameter epsilon, which is the difference between DC and the physical dimension, as long as epsilon is small enough to justify such a perturbative expansion. Okay, so we applied this technique to various non-Fermi liquid systems, and the simplest one of them was the Ising nematic quantum critical point. So for this quantum critical point, we have a phase transition between two phases where the Fermi surfaces have different symmetries. So in the first phase, the Fermi surface has a Z4 rotational symmetry. That means it looks like this square. Whereas in the other phase, the Fermi surface has a reduced rotational symmetry, which is the Z2 symmetry. That means it is stretched either in the vertical or in the horizontal direction. Now, in the first phase, the order parameter takes a 0 expectation value, whereas in the second phase, it takes a non-zero expectation value. And let me just point out that the order parameter phi in this case is a real scalar boson, which becomes massless right at the quantum critical point. And this kind of ordering is believed to be present in various kind of high TC materials. And schematically, it is shown that how nematicity can appear in their phase diagrams. Now, let me just tell you the results that we got. We considered this Ising nematic quantum critical point in generic dimensions, but the two-dimensional case is interesting due to the fact that it is related to this high TC materials phase diagrams. So for the 2D case, we have a one-dimensional Fermi surface, which which undergo violent fluctuations, but these fluctuations are effectively local in momentum space. Now, focusing in this strange metal regime, we computed the optical conductivity sigma as a function of omega, where omega is the frequency of the applied AC electric field. We found that it goes as omega to the power minus 2/3. And this value is quite close to the value found in various experiments carried out on optimally doped cuprates. Next, I decided to look at the competition between the non-Fermi liquid phase and the pairing instability at 0 temperature. And my results showed that superconductivity always wins. And this explains the fact that why generically in experiments, we do not see a naked quantum critical point, but we always see a superconducting dome hiding it. Now, we also looked at the 3D Ising nematic quantum critical point system. For the 3D system, we have a 2D Fermi surface. Now, this 2D Fermi surface undergoes fluctuations which turn out to be non-local. That means these fluctuations are entangled with each other along the entire Fermi surface in the momentum space. But of course, these fluctuations are less violent than the 1D Fermi surface case. It's a marginal Fermi liquid actually. Now, we also found that there is this curious emergence of the mixing of ultraviolet and infrared physics, which I'll explain to you later. And this leads to the fact that the results that we obtained were one loop exact. That means the two loop and the high loop corrections all vanish for this system. Now, there are other systems where we applied similar formalism. And one example was the quantum critical point lying between the FFLO and normal metal transition. So here for some organic materials, we have an homogeneous superconducting phase, and then it goes to an FFLO superconducting phase, and finally it goes to a normal metal. And it is expected that there might be a quantum critical point at this region. Now, let me remind you what I mean by FFLO Cooper pairing or the FFLO superconducting phase. Now, for normal superconductor, we know that the Cooper pair has zero momentum because the electrons that are pairing has plus k and minus k momentum, equal and opposite momentum. But for an FFLO phase, what happens that there is Cooper pairing with finite momentum, which is equal to Q FFLO. So from this diagram, we see that this electron is pairing with another one, and that electron is pairing with another one, and there is a net momentum for each pairing. Now, this system was interesting for us because it has the potential of showing up a naked or unmasked quantum critical point, because there might not be any competing order parameters which might just obscure or hide this quantum critical point. So if the experimentalists can observe this, then we might be able to find scaling regime observable down to arbitrary low temperatures and actually see a quantum critical point. So for this system also, we computed the critical properties of the stable non-Fermi liquid, which might arise here with the controlled approximation, which I explained to you. Now, there are other examples where I considered Fermi surface interacting with one or more transverse gauge fields, or Fermi surface interacting with the spin density wave order parameter. Now, let me give you some technical details for solving this Ising nematic quantum critical point. So as I told you, we took the generic Ising nematic system in generic dimensions. So let us take an m-dimensional Fermi surface interacting with a scalar boson. Now we are interested in formulating the low energy effective theory. And in this low energy limit, fermions are allowed to scatter only tangential to the Fermi surface. This is because if the fermions scatter perpendicular to the Fermi surface, that will cost a lot of energy, and we don't want to keep those processes in our low energy field theory action. Now, we will also assume that the system has time reversal invariance. That means if we have a fermion, a right moving fermion, we must also consider its left moving counterpart. Now, let us look at a 2D Fermi surface, 2D system, which is a 1D Fermi surface. Now, here we have a circular Fermi surface, which is one-dimensional. So M is equal to 1. Now, if we consider the blue fermions, then they do not interact with the red fermions, because if they want to interact with the red fermions, then this condition that fermions should scatter tangentially, that cannot be satisfied. So this leads us to the conclusion that for this 2D system, fermions in different patches are decoupled except at the antipodal points where the momentum are parallel, or the tangential momentum are parallel. But this argument will not hold if we move to higher dimensions. For example, if we go to 3D, which has a spherical Fermi surface, then any 2 points can be joined by a series of tangent vectors. So basically, therefore, if we take fermions scattering at any 2 points on the sphere, they can scatter with each other, maintaining the condition that their momentum is parallel to the Fermi surface. So this patch argument is not true for an m-dimensional Fermi surface with m greater than 1. So when we started our calculation, we expected that somehow the size of the Fermi surface, which is encoded in kf, that should enter in the various physical quantities as a dimensionful parameter. Now, let me try to emphasize on the significance of the various dimensionalities we have in the system. Now, we know that there is this overall spatial dimension d, and if we increase d, the quantum fluctuations become weaker and weaker. And that's what I explained to you while explaining the dimensional regularization philosophy. Now, there is this other dimension m, which is the dimension of the Fermi surface. If we increase the dimension of the Fermi surface, then the gapless modes become more and more entangled with each other. Right at m equal to 1, the observables are local in momentum space. I mean, there is no entanglement with each other. Therefore, physical properties like the Green's functions can be extracted from local patches. And there is an emergent locality in the momentum space for this m equal to 1 systems. However, if m is greater than 1, there is this emergence of the mixing of ultraviolet and infrared physics. And why do we say that? Because I told you that I want to write down the low energy effective field theory action, but now we see that this low energy physics is being affected by gapless modes, which are extending over the entire Fermi surface. And the extending over the entire Fermi surface means that is the ultraviolet physics. And this gives rise to the mixing, leading to the fact that the size of the Fermi surface, kf, modifying the night scaling, which you would have obtained by just focusing at local patches. So somehow the kf becomes a naked scale because it shows up in various physical properties. Now, to set up the action of the system, we need a suitable coordinate system. Now, we can erect the coordinate system by taking any point on the Fermi surface. Now, this will apply to a Fermi surface of arbitrary shape, but as long as they are convex. So let us then.
Can I ask you something?
Yeah, go ahead.
Which is related with this, like a UV-IR mixing you are referring to?
Yeah.
So what do you mean exactly with that? I mean because so are you meaning with that your effective theory has to be like a non-local theory?
No.
Because
the effective theory is always local in real space, so there is no question about it.
Is the okay? There is. You're assuming locality.
So the entanglement I'm talking about is in the momentum space.
So okay, but then that's the point. So you're assuming that there is locality in real space.
Yeah.
But then you are mentioning that mixing, that UV-IR mixing. So how can you understand that in quantum theory terms? Because
so that's exactly what
I
am trying to explain it to you. So it's in condensed matter theory, kf is the highest scale and kf is taken to infinity. So we don't expect kf to appear in various physical quantities. But here, due to the excitations talking to each other over the entire Fermi surface, kf will appear in your physical observables. So that's what I mean by physical, by UV-IR mixing. So somehow the kf scale, which refers to the UV scale, is interfering with the low energy physics, where we were sending kf to infinity.
Right? Okay, I may ask again at the end.
Yeah, so just keep in your mind that the UV scale is the kf scale, which we should send to infinity. And so if kf appears in our physical observables in the low energy effective field theory, that means that UV scale is somehow coming into our observables, and there is a mixing of low energy physics and kf. So this is what I mean. I mean, there is nothing else. So you should not also confuse the locality in momentum space with the locality in position space. So the theory is absolutely local in position space. But here I'm talking about the entanglement of the gapless modes, which is appearing in the momentum space when you are taking m greater than 1.
Okay. Okay, thanks.
Okay, so I was talking about how to erect the coordinate system. So we choose a particular point, say k star on the Fermi surface, and then erect our coordinate system. At this point k star, kd minus m is the local perpendicular, which is measured with respect to the local Fermi momentum. And then the tangential directions are indicated by this vector L of k, whose components are giving us the various tangential directions. Now, since I told you that we will assume that we have a time reversal invariant theory, so if we take a right-moving fermion labeled by psi plus at k star, we must consider the left-moving counterpart, which is appearing as psi minus and at minus k star. Now, the fermions are labeled then by psi plus or minus, and then there is an extra flavor index j. Now, j can be anything. It is not a control parameter in the theory, so it does not matter what j you choose. So what j you have will be dictated by what theory you're looking at. For example, if you take a theory view where you have up and down spins, then j will take the value 1, 2, etc. But anyway, it is just a spectator variable and does not play any part in the control of the theory. Now we are ready to write down the effective action. So we have two halves of the m-dimensional Fermi surface. One half is centered at k star and another half is centered at minus k star. And these halves are interacting with the massless boson in d space and 1 time dimension. And the physical dimension is equal to m plus 1 because we are considering an m-dimensional Fermi surface. And there is one direction, one perpendicular direction. So the total spatial dimension is equal to m plus 1. So here I have written down the action. The first line is just the kinetic term for the fermions, the plus and the minus fermions. Now we have expanded the fermionic momentum around that point in the Fermi surface. Now we can just forget about the higher order terms in L because these are irrelevant in the renormalization group sense. The second term is the kinetic term for the bosons. It's massless, so there is no mass term. And the third line indicates the coupling term between the fermions and the boson with the coupling constant E. Now, basically, we have made the fermionic dispersion parabolic because we have just kept up to the terms Lk square and discarded the higher order terms. But physically, of course, the Fermi surface is compact. It's not a parabolic one. So we have approximated the compact Fermi surface by two sheets of non-compact Fermi surface centered at plus minus k star. So while doing the momentum integrals, we must be careful of this fact. So we can take care of this non-compactness or superficial non-compactness by using a soft momentum cutoff. So we'll keep this finite size of the Fermi surface in our integrals by damping out very large Lk modes, which are far away from plus minus k star. And this soft cutoff is employed by using an exponential damping factor. So now we will rewrite the action that I just showed you in terms of this two component spinor, which is indicated by capital psi j. And these components are psi plus and psi minus dagger. So we just rewrite the action that I showed you in terms of this two component spinor. And now it takes this form. Now gamma 0, gamma 1 are just Pauli matrices. Now if we interpret the L of k as a continuous flavor here, then each of this original m plus 2d spinor can be viewed as if it were a 1 plus 1d Dirac fermion. So the reason that we rewrote in this form is that it looks like the action of a Dirac fermion, and now we can use the entire machinery that is available for us from the quantum field theory of high energy physics for this kind of fermions. But that was the original action. But now to perform dimensional regularization, we have to add some extra dimensions perpendicular to the Fermi surface or perpendicular to the Lk momentum. So superficially, we can then, we are increasing the total dimension of the system above the physical dimension. So we are doing this by promoting K0 to a vector capital K, which has many components, depending on how many dimensions we are adding. And then this gamma 0 matrix is promoted to a vector of gamma matrices. We are also relabeling gamma 1 as gamma D minus M, and delta K is a shorthand notation for this combination. So now our action for the fermions looks like this, and it looks like a higher dimensional Dirac fermion. And now we are ready to deal with the dimensional regularization to find the upper critical dimension. Now, we are using dimension as a tuning parameter in our theory. And let me remind you, if the overall dimension or the actual physical dimension is less than the upper critical dimension DC, then the theory flows to an interacting fixed point. Here, it's a non-Fermi liquid fixed point at low energies, and we cannot explain it by a Fermi liquid theory or a mean field picture. But if the physical dimension of a system is greater than DC, then it could have been well described by a Fermi liquid picture. Now, when we choose a regularization scheme to regularize divergences in the theory, in order to get a systematic renormalization group equation, in relativistic quantum field theory, usually we are careful that we maintain locality in real space, and it is the effective theory is consistent with the original symmetries of the system. Now, in our case, our dimensional regularization scheme, we have the advantage that we still maintain locality in the position space. We do not touch it, but there are other alternative schemes to deal with this non-Fermi liquid systems where they break locality. An example will be Senthil and Sankar in their work in 2009. However, we have a small disadvantage that we had to break the global U1 symmetry, but that does not affect any of our physical results when we continue to the actual dimension. Now, let me also remind you about the energy scales that we have our theory. So I have talked a lot about ultraviolet, infrared mixing, and so on. So let us try to identify these scales. Now, we have a Wilsonian cutoff lambda, which is the implicit Wilsonian UV cutoff, such that all the momenta in the theory, all the perpendicular momenta, which is this capital K and KD minus M, these must be much less than the Wilsonian cutoff lambda. On the other hand, this Wilsonian cutoff must be much less than the Kf, or the Fermi momentum, which is taken to infinity in a condensed matter systems. So basically, Kf sets the size of the Fermi surface, which is taken to be infinity. And then this lambda sets the largest momentum that the fermions can have perpendicular to the Fermi surface. So using lambda, we derive the renormalization group flows. That means we change lambda and require that the low energy observables are independent of lambda. So this gives us the beta functions, which give us the RG flows. Now, to find out the upper critical dimension, we fix M and then find out the DC, which is the dimension at which the fermion self-energy diverges logarithmically. That means if we compute this diagram, this loop diagram, then the value of D, where it shows logarithmic divergence, is the value of DC. So in this way, by identifying the DC, we can access the non-Fermi liquid perturbatively in the small parameter epsilon, which is the difference between DC and the physical dimension. And remember, the physical dimension is M plus 1 because we are considering an M-dimensional Fermi surface, and there is a direction perpendicular to the Fermi surface. So by employing this method, we could identify the upper critical dimension, and it gave us the value M plus 3 by M plus 1. So for a three-dimensional system, which has a two-dimensional Fermi surface, or M equal to 1, DC is equal to 3. That means now epsilon is equal to 0, which is a marginal Fermi liquid. Now, for a two-dimensional system, which has a one-dimensional Fermi surface, or M equal to 1, DC is equal to 5 half. So epsilon is equal to half for this system. Now, if we compute the scaling dimension of the coupling constant E, that is given by this expression. And by putting in the values, plugging in the values, we see that E has a positive scaling dimension at DC. So if we put D equal to DC and set M between 1 and 2, then E has a positive scaling dimension. So its scaling dimension does not vanish at DC, and therefore it cannot be a control parameter in perturbative loop expansions. So we have to find a suitable control parameter, a suitable coupling constant, whose dimension vanishes at DC. And this is given by E effective, which is E raised to a certain power divided by Kf raised to another power. Actually, this is Kf tilde, and Kf tilde is Kf divided by the Wilsonian energy scale. Now, if we compute the scaling dimension of this E effective, then it is proportional to dc minus d, and this is equal to 0 at dc. And this tells us that this E effective should be used as the effective coupling that can serve as the control parameter, which remains small in value in loop expansions. So then we work with this effective coupling, and we find out the beta function for this effective coupling.
You have 5 minutes.
Okay. And the zeros of this beta function helps us to identify the fixed points of the theory. Now we have the Gaussian fixed point and we have the interacting fixed point. We are interested in the interacting fixed point, which has the non-Fermi liquid behavior. And at this fixed point, we find that E effective takes this value, which is proportional to epsilon. And remember, the epsilon is the difference between DC and the physical dimension. And we also computed the dynamical critical exponent and the anomalous dimensions for both the fermions and the bosons at this interacting fixed point. Now, we also can show that this interacting fixed point is a stable fixed point. That means the RG flows are towards this fixed point, whereas the Gaussian fixed point is unstable because the flows are away from it. Okay, and then we also computed the higher loop self-energies for both the fermion and the boson. Let us first look at the two-loop bosonic self-energy. We found that for the m greater than 1 case, the answer is Kf suppressed. That means when we take Kf going to infinity, the correction goes to 0. So here is the expression where we see that there is this extra factor compared to the one-loop answer, which depends on this Kf in the denominator, which tells us that this loop correction just vanishes when we take the Kf going to infinity limit. However, for m equal to 1, there is no such Kf factor and we get a finite correction. So there is no UVIR mixing for the m equal to 1 case, but such a mixing occurs for m greater than 1 case due to the appearance of this Kf factor. Now, similar story goes for the two-loop fermionic self-energy. The answer is too long, so I did not show you the expression, but the main point is that for m greater than 1, the answer is Kf suppressed and it goes to 0 as we take Kf to infinity. However, for m equal to 1, there is no Kf factor and we get a UV divergent answer. Of course, we cannot evaluate to all loops, but from generic arguments, we can always argue that for m greater than 1, these answers will always be Kf suppressed, so that for m greater than 1, the answer is one loop exact. However, for m equal to 1, we have to go on correcting the theory in a perturbative series. Okay, so I think I will just stop here because I don't have much time. I will not talk about the pairing instabilities, and I will just skip this part. And let me just go to the summary. So I explained to you a renormalization group analysis for the critical Fermi surface. And I showed you that how the scaling behavior of this non-Fermi liquid states can be extracted in a controlled approximation via dimensional regularization. So we took a generic m-dimensional Fermi surface with its codimension extended to a generic value. In this way, we could identify a stable non-Fermi liquid fixed point using the epsilon expansion, where epsilon is the difference between DC and the physical dimension. And this can be used as a perturbative parameter. Well, I did not talk about the pairing instability, but the key point to take away is that Kf enters as a dimension full parameter, unlike in relativistic QFT, when we are looking at m greater than 1, and then it modifies naive scaling arguments. And the effective coupling constant, like we saw, the E effective, which can be used as a controlled parameter, that is a combination of the original coupling and some factors of Kf for m greater than 1. And thank you for your attention.
Okay, thank you very much for the very instructive seminar. So it's time for questions. So if anybody has a question, please unmute yourself and pose your question.
If I can, how about finite temperatures?
Oh, the
there any
finite
chance that
temperature is a
will-
mess. That calculation is very difficult. So people have used various kinds of methods like memory matrix, quantum Monte Carlo, etc. But all these methods they have some problem or the other. They're not trustworthy. I have not performed any finite temperature calculation for this system.
Okay, but is there any chance that the dimensional regularization can work at finite temperatures?
Well, this is only a zero
because
temperature
non-Fermi
one,
liquid
right?
behavior is very important at high temperatures. For example, the linear temperature resistivity. This is what we would expect to be able to somehow derive.
Yeah, you can expect to derive, but you have to formulate a method to derive. Of course, dimensional regularization cannot be applied for the finite temperature case because at zero temperature only, your dimension becomes continuous and you can treat the temperature dimension as a continuous variable and you apply these methods. At finite temperature, as I told you, it becomes messy because then you have a Matsubara sum rather than an integral over omega. So that becomes messy. And as I told you, there are various efforts and people do find the linear t or t to the power 2/3 behavior by those methods, and that those are controversial, but those include things like as I told you, quantum Monte Carlo or memory matrix, etc. Memory matrix, I think, is quite a well accepted method, and that gives you this t behavior.
Okay, thank you very much.
I would have a similar question. I mean, you shown data for a certain point that you have calculated optical conductivity, which
Yes.
goes as 1 over omega to power 2/3. Is it also the zero?
So that is actually, that can be computed by using this theory that I told you, because that is in the limit where omega h is greater than t. So the optical conductivity limit can be computed because that's the sorry, what am I saying? Yeah, that is the omega greater than t limit. And then we are still using this continuum theory without using the Matsubara frequency. So we can extract the optical conductivity by applying the Kubo formula at very low temperatures, assuming that we are still allowed to use the integrals rather than the Matsubara sums. And for some cases, we can find out the scalings from there. But of course, this is not valid at finite temperature. You can use some dimensional argument by saying that, okay, at higher t, where this theory we cannot use anymore, we have to use the finite t Matsubara sums, we can say that this omega scaling will be replaced by a t scaling. So that will go as t to the power minus 2/3 rather than omega to the power minus 2/3. But those kind of heuristic arguments you give, but yeah, you really have to do a different calculation to look at finite t. But for omega greater than t, this formalism is still valid, and that's what we used.
So what is then the physical interpretation of this data? Because you get singularity at zero frequency at finite temperature, and what does it mean?
It's omega greater than t, so you're not allowed to take omega going to zero, right?
Okay.
So if you want to compute DC conductivity, as I told you, there are people have computed that using methods like memory matrix or quantum Monte Carlo.
No, I know. Okay. This is I missed this point. So this is valid only in the for large frequency, essentially.
Yes, omega greater than t limit.
Okay. Thank you.
Any other question? Okay, I have a non-technical question.
Yeah.
That I mean, I think I've heard like Jan Sanning in some kind of recent talks arguing that from some recent experiments, we already know that there is no quantum critical point hidden under the superconducting dome in cuprates, but I never understood the argument. Do you have a comment? Do you have
I
a
don't know
comment?
about
Are you
those.
aware of it?
No, I'm not aware of it. I don't know about that.
Okay, yes, because I think him like insisting that we already know that this thing is not there, that there is no quantum critical point. So, but yeah, I don't know.
I think you cannot prove or disprove it, right? Because it's you cannot reach zero temperature.
I mean, yeah, my point is I don't know the argument. I don't know what's the argument. I don't know exactly
I
what
also don't know.
experimental evidence he mentioned.
Okay.
But what I'm sure is that he was just like insisting, and he's emphatic when he, well, I guess you know how he is. Okay, so any other question in the audience? Well, if not, then we thank Ipsita again. So thank you very much for
Thank you.
attending our virtual talks. So I will stop now the recording.